Cool. Welcome everyone. Good morning. Welcome to the ElastiCache Silent Disco. Glad you could make it early in the morning, and welcome to reInvent. Thank you for coming. We're going to be talking about ElastiCache Serverless. We will talk about how you can implement caching in a serverless architecture, and we will go into details about how we built ElastiCache Serverless and the improvements we've made over the last year, just to give you a glimpse into how it all works under the hood, so you can have a better understanding of how it works and how you can use it in your applications. So let's first start with what is caching, right? In its most basic form, you put something where you need it quickly, right? Because you don't have the time or the latency to go pick it up when you need it urgently, right? So that's really basically what caching is. You put something in a readily accessible place, which can tolerate high frequency of usage, and something that can offer really low latency of getting that data. So you would ask why cache, right? The most basic reason why you would cache is really to help reduce latency. So here's your basic serverless architecture. You have your client talking to an Amazon API gateway, talking to some kind of compute, in this case Lambda, and then some kind of data storage, say DynamoDB. And there are multiple cases or multiple reasons why your application might be running slow, right? So for example, your database might be slow because you've got a really expensive query, or it's just overloaded under a lot of traffic. You can have network traffic. Your network might be congested because and adding up to latencies, right? So there's many reasons why your application can be running slow, and a cache can help reduce that latency. The other reason why you typically cache is when you have a read-heavy workload, right? Typically what you would do if you've got a lot of reads, your application is reading the same thing multiple times. Imagine, session data, for example. A user is using your e-commerce application and they're reloading the page multiple times. You don't want to have to reload their session data, like card data or login information, etc., multiple times from the database. What you might do here is you might add multiple read replicas in your database, but that can become expensive very, very quickly, right? And so instead, what you could do is you could add a cache, right? And you store that data in a cache, because a cache can help you scale reads much faster, as well as at a lower cost, right? Where you're not paying for read replicas in your database. So let's jump into why you would cache, right? Or rather, how you would cache. There are multiple things to think about when you're adding a cache in your serverless application, right? So we will cover all of these topics here that you see on the screen. So let's jump right in with caching strategies. There are various caching strategies you can employ. The most basic one, or the one that most people start with, is called cache aside or look aside caching. Here, essentially, your compute system is reading from the cache, and if you get the data from the cache, great, you serve up your application. If you don't get that data from your cache, because it's called a cache miss, you read that data from the database, and then you write that data back into the cache, and that's essentially look-aside caching. Think of it as a sidecar pattern, right? It's the benefits of this approach is it's simple, right? You don't really need to deploy any specific logic to your database. It's straightforward. You can have your cache live in a separate location, separate system, and it's very simple to deploy in an application. Your application logic changes are somewhat straightforward, right? You can also control your cache size. Your compute layer controls what you put into the cache, right? So that way you can control how big your cache becomes. There are some disadvantages to this approach, right? Your first read is almost always going to be slow, because you're going to have to read from the database. That data there is no hydration unless you implement specific logic to hydrate your cache, right? And implementing data consistency is difficult, right? Because now you've got data stored in two different places. You've got data in your database, and you've got data in your cache. And so maintaining consistency between these two sources is somewhat difficult. And we will cover consistency strategies in a bit as well. The other approach is what is called a write-through cache, right? So here, data is written to both the cache and the database at the same time. So the benefit is that your data is in the cache is almost never stale, because you're writing to the cache and the database at the same time. right? And so the consistency is somewhat better because you're writing at the same time. And so when one is updated, say the database, you're also updating the cache at the same time, right? And generally, there is a less likelihood of a cache miss in this scenario. The disadvantages is, of course, your writes are going to be slower because now you're writing to two systems, right? You're writing to a database and you're writing to the cache, and so whichever is the slowest of the two, in most cases, the database, but your writes are going to be slower, right? And this also means somewhat often ignored disadvantage that your cache size can be extremely large because every piece of data written is being written to the database as well as to the cache, right? And so your cache can balloon because all of your data is now in the cache. The other approach is called write behind caching. This is somewhat of an improvement or an optimization on the write through caching approach, where you write the data to the cache first, and then you respond back to the application. And then at a later time, asynchronously, you write that data to the database at some point. So this way, your writes are faster because your writes are no longer being, waiting on two data commits. You're writing to the cache, which is usually fast because you're writing into memory, and then you respond back to the application. Right, so you have better write latency, and it is very useful for applications that have higher write throughput, right? Because if you're writing very, very frequently, you can just write to the cache and then asynchronously write to the database. Now, the downsides are somewhat obvious, right? It is complex to implement. Now you have in your compute, you need to implement an asynchronous write strategy, right? You need to have something which doesn't drop the writes, right? So your writes are written to the cache, and you need to make sure that it is written to the database at some point in the future. There is some risk of data loss because you're writing asynchronously, data can be lost, right? You're only writing to the cache, and if for whatever reason your compute fails and you're not able to write it to the database, your data could be lost, right? And data inconsistency is also a possibility because now you're writing asynchronously, that can lead to inconsistencies. So let's talk about consistency, right? We've spoken about how you can implement caching. These are the various basic versions of caching strategies. Cache invalidation or caching consistency, data consistency is hard. It's not an easy problem. It's not a solved problem. There are trade-offs, right, that you will have to consider. So let's go through them. The most basic version of cache invalidation and ensuring consistency is time-based. So you essentially, when you are reading from the cache, you get what is a cache hit, and then after some time, your time to live on the cache data expires. So you can set, in most caches, in ElastiCache Serverless, for example, you can set a time to live on every piece of data, and after that time, the cache automatically evicts that piece of data, and you would get what is a cache miss, right? And when that happens, you read from the database, and then you write it into the cache, right? So that's just basic cache invalidation based on time. Simple to implement, right? Most caches give this to you out of the box. You set a time to live on the piece of data, and it will be evicted after some time automatically. Although it can be complex to implement in terms of what is a reasonable TTL to choose, right? Now it is oftentimes more judgment based, even though you can have some logic there, right? Like imagine you've got session data of a user logged in. Now you can have some reasonable time to live on that, right? Your sessions generally last, say, a few minutes, so you can set a time to live of, say, an hour. You don't want the user to log back in after an hour or something like that, right? So, but deciding on the time to live, depending on your application, could be difficult, right? And it is difficult to manage consistency between your database and the cache because the data is not going to be evicted until the time to live expires. And so if something changes in the meantime in the database, your data will be inconsistent until the cache data is evicted. The other one is event-based invalidation. Here, essentially, you build a separate system for invalidating your data. In this case, as you can see on the screen, we have a new compute Lambda layer, which is reading DynamoDB streams to consume the changes in the data. And when the data is changed, this Lambda will invalidate or update the cache data in the cache. Right? So you have a separate system which is doing this for you. This essentially achieves faster consistency, right? It is still asynchronous consistency because your data is updated in the database. You get a event into your compute system, which then updates the cache. So it's asynchronous, but usually pretty fast, right? Generally of the order of milliseconds, maybe seconds. But you achieve much faster data consistency than the time to live approach. And this only evicts data when there are any changes in the underlying database. However, this adds complexity to your implementation. Now you've got a separate system which is doing your cache invalidation. You have to test the system, deploy the system, so it adds some complexity to your application. And it is generally when you add more systems to your architecture, you add complexity not just in terms of the code, but also in testing, making sure things work end to end. And it is especially difficult in an asynchronous system like this, where you are depending on streams and asynchronous updates from the database. The most complex version, but also the most precise version in this presentation that we'll cover, is what is called version-based invalidation. If you haven't used this already, the way this works is essentially you maintain a version of every key in your cache. Right? And this way, anytime you're reading the key or reading data, you make sure that you're reading the latest version of that key. Right? And this way, especially in a system which has high throughput with compute systems trying to talk to your cache at the same time, this gives you a much higher level of consistency, right? So essentially, you get the version, you read the data of that version, and that's how you do reads, right? So you first get the read, you read the version of the key, and then you read that version of the key from the cache. When there is a write, essentially you first update the version of the key, and then you essentially you're updating the version of the key so that the next read is going to read the latest version of the data. So that way you have much faster consistency of data. Now, as you can imagine, this is somewhat complex to implement, right? Now you need to implement this logic in your compute system. Most caches, like ElastiCache, don't give you an out-of-the-box support for versioning, even though you can implement it yourself, right? So you can always set data, you can set the version of the key inside the cache and maintain both the data as well as the versioning of the keys inside the cache. But it does add complexity of implementation. But if your application cannot tolerate stale data and you need stronger consistency between the database and the cache, this is a great way to do it. So we covered caching strategies and we covered cache data invalidation. Now let's talk about how to store data in the cache, right? So we will cover a few use cases and we will talk about how you can use ElastiCache Serverless to store that data. The basic version of most applications that start with caching would be session management. You want to store your user session data inside your cache. So typically the way that would work is you would essentially have that data be stored in the cache in a hash data structure. So ElastiCache Serverless supports Valkey and Redis OSS. We will talk about both of these engines in a bit, but we support Valkey and Redis OSS, which support advanced data structures like hash, where essentially you can store multiple levels of data or multiple sub values, if you will, inside that key. So you have a key here, which is the session user 123, and then you have multiple types of data stored in there. So you have the auth token, you have the last login, you have the preferences. You could also store it in JSON format. ElastiCache Serverless supports the JSON format, which is a more structured format, and this way, it also storing it in JSON format gives you the ability to search through data easily and also support updating sub parts of the JSON document. Right? So you can use either of these data structures to maintain your session data. The other frequently used pattern in serverless architectures is rate limiting, right? And it is not generally obvious that you could use a cache for rate limiting. Essentially, the way this works is, you want to limit, for example, access to a precious resource. In this case, I'm showing a database. It could be anything. Could be a service call, which is expensive, or anything which you want to limit access to or limit how frequently a user can access it, right? So you essentially simply maintain the data as a string in your cache, and you increment the counter every time somebody accesses that resource. Right? And so, as long as your request count is below that value in a given time frame, you can allow access. And the way you control the time limit is through a TTL. You set a TTL on the value. Let's say you want to limit to, let's say 10 accesses in a 5-second period, right? Or 10 accesses in a 5-second period. You set a TTL of 5 seconds, and then you just increment every time somebody accesses it. And when that count exceeds your value, in this case 10, you simply deny access. Right now, in this case, I've shown an access count of 2, imagine this is whatever that value is that you want to limit access to, and you simply deny access. So rate limiting is generally important in serverless architectures, where you want to make sure you preserve how many times somebody accesses a precious resource, and you can do that easily using a serverless cache. The other one is caching expensive computations. Right? Typically, if you're using, let's say, a relational database, right? In this case, I'm showing a query which is, for example, pulling product details from your inventory based on what's on discount and based on what has high reviews for your e-commerce application, let's say. As you can see, right, this is doing multiple joins across multiple tables, and this can get expensive very, very quickly. And it can take a lot of time on your database, and also it can take up a lot of resources on your databases. But as you can see, if a user is looking at the details of this product on your website, and they're refreshing the page or coming back and forth to it, the data isn't going to change that frequently. Right? So this is a great candidate for something to be cached, and this is an expensive computation that you could cache in your cache. Right? So essentially, you store this data as a JSON document. In this case, as you can see, we've essentially gotten all of the product details, stored them as a JSON document, and as you can set a TTL. Right? Assume, for example, that your product inventory doesn't change within 5 seconds or 10 seconds or even a minute. Right? Depending on your application, you set a TTL. And that way, you've dramatically reduced the load on your database by storing this expensive query result in your database. The other one is leaderboards and rankings, right? So you've imagine you're building a gaming application. You want to store the data about your top users. You can store that in sorted sets. If you're familiar with Valkey and open source Redis, I'm sure you're familiar with these data structures, but just wanted to cover the various data structures that are supported in ElastiCache to store different formats of data. So we covered some of these details about how to cache, right? So you've got caching strategies. We covered the look-aside pattern, write through, and so on and so forth, how to invalidate data and maintain consistency, and how do you store data, right? So that's generally the basics of caching. Now let's get into some of the infrastructure pieces of cache, right? So when people set up a cache, you also need to think about how you set up an infrastructure for your cache. And this is where a managed service like ElastiCache Serverless comes in, right? We can help you do a lot of this automatically behind the scenes because that's what we're focused on, right? So, sorry, there's some background noise. I don't know if everyone can hear it, but let's talk about performance at scale. We've invested a lot in achieving high performance with ElastiCache Serverless, right? We support multi-AZ data replication, and we support low latency read traffic when you do read from replicas, right? So we have intelligence built into the system where when your application is reading from ElastiCache Serverless, we detect which availability zone your request is coming in, and we route that to the local AZ proxy node and make sure that you get local AZ read performance, right? This also gives you, we are able to scale from 0 to 5 million requests per second, and that 5 million requests per second is, we can scale from 0, where your application has no reads, to 5 million requests per second within minutes, in under 13 minutes. And we will talk about how we do that in a second. Yaron's going to cover how we can achieve, how we achieved this speed. We are able to double your request throughput every 2 minutes, right? When we launched this last year, we announced this at reInvent last year, we were able to double throughput once every 10 to 12 minutes. And in the improvements we've made since last year, we can now double throughput every 2 minutes. And we will talk into how we achieved that in a second. But really, just here's you might have seen this, in our documentation. But this diagram sort of gives you a high-level view of how things work under the hood. And then Yaron's going to go much more into the details. But we've got a proxy layer here that is serving the requests for ElastiCache Serverless applications. So your client application talks to a single endpoint, and the requests are routed to the local AZ proxy nodes. And behind the scenes, we automatically control scaling for you. We scale both vertically to give you instantaneous burst capacity, and we scale horizontally to give you more capacity over time. That's the doubling capacity every 2 minutes that I was talking about earlier. So this gives you really high, really fast performance and high throughput at scale, right? So we can support really high scales really, really quickly. The proxy architecture has other benefits listed on the screen, as you can see. Because you're talking to a proxy layer, we abstract the underlying cache node topology and the changes to the topology from your application. So your applications, for example, don't get disconnected from your cache anytime the topology changes, because you're connected to the proxy node, and the proxy has intelligence to maintain connections to the cache nodes very, very quickly as they change. This also gives us the benefit to apply software patching automatically and transparently. We can apply and update all the minor and patch versions of the cache automatically, transparently, without any impact to your application. The other important piece when you're deploying a cache is capacity management. When you're deploying a cache, you need to think about how much cache capacity you will need. Typically, what you would have done, for deploying a cache capacity is you would look at what your peaks look like over a certain period of time, say last, 6 months or 1 year, and you would provision enough capacity for those peaks. But what would happen when you exceed those peaks, because you have new peaks, is you would not have enough capacity, right? Or you would have to manually scale the cache at that time. And you're paying for cache costs which are underutilized when you don't have those peaks. But it's not just that. Capacity management is even harder than what it looks like, at first blush. Because what you would have to do is you would have to look at what is your data set size. And as we discussed previously when we were talking about this, depending on your caching strategy, your cache size can be as big as the database, or it could be a subset. But deciding how big your cache can get is difficult without actually running your application, running tests, or actually, performing significant calculations to figure out what your cache size might look like. So deciding how much memory you need is not easy. Then deciding how many requests per second you might have on your cache, or how much throughput you would have on your cache, can result in different compute requirements, right? So you might need a higher compute if you have really high throughput, right? Your command complexity can result in different amounts of compute capacity needed, right? So imagine we discussed the leaderboard example, for example, right? And if you have an application that is constantly trying to find the top 3, say, players from hundreds of thousands of players, that is an expensive computation. Even though it is happening in memory, it can take time. And if you're doing that at high throughput, that will require a lot of compute. That's a compute-intensive application. Your payload size can result in different levels of network requirements. Your connection requirements can result in different network requirements, and so on and so forth. So deciding how much capacity you need on a cache is not straightforward. Let's just put it that way. And serverless essentially gets rid of all of that for you. So ElastiCache serverless is designed on the principles of no capacity management. We don't want you to have to think about capacity management at all. We essentially make sure that we scale behind the scenes as your application grows, and we scale back down when appropriate internally. But it doesn't really matter when we scale in or scale back in the capacity, because you pay for use. So built on serverless principles, we wanted to make sure that ElastiCache serverless offers true pay-per-use pricing. So you always pay for memory. So any data that is stored in memory, you pay for that. And any requests you execute on your cache, you pay for those requests. And that's it. So when you're not executing any requests, you don't pay for any compute. So we've covered a lot at a high level of how serverless can help you achieve some of the basics of deploying a cache, and we covered how you can achieve caching in your applications. Let's now go deeper into how serverless works. Hopefully this will give you a glimpse into how things work under the hood and help you understand how you can utilize serverless ElastiCache better for your applications. I'm going to hand it over to Yaron. Thanks, Yaron.
Thank you very much, Abhay. Hello, everyone. Thank you for joining us today. It's really great to be here for me. I'm super excited to talk about serverless every time, and the reason is because my team built actually the technology behind this great product. So I want to dive deep today to tell you how we solve all the challenges. So let's start. Let's start from the high-level architecture, and then I'm going to dive deep into each of the components that I'm going to speak with. First, your application is running on your VPC and connected to the service VPC. It's go through the endpoint that we provide you, which you go through first through the node balancer that balance the connection across the proxy fleet. I'm going to speak about the proxy a bit more in the next few slides. And then the proxy is responsible to route the request to the correct shards. So it's actually encapsulate all the connectivity from your point of view. But it's much more smarter than that. The proxy used multiplexing connection. So we actually have a single channel, TCP channel, that can send multiple different client connections. So every time that we operate network batch, we can use less system calls. So this is first improves the performance, and eventually it helps us to maintain less connections to the storage nodes. Besides that, as you can see, our architecture is spread across multiple AZs. So one, if we support high availability, of course. If one of the AZ is failing, you still have access to your data store. And we can promise you microseconds response time because we use the Route 53 to locate the same raw proxy that is on the same AZ that your application is running. So you might be surprised, behind the serverless, there are a lot of servers that run in. And our job is to manage them properly and to scale them every time that you need the serverless to grow the workloads. So let's start from the cache nodes. The cache nodes running on a multi-tenant environment. And there are shared resources like CPU, memory, and networking. And our job is to monitor every time to make sure that you have enough capacity, enough resources to run your workloads. So let's zoom a bit more and see. We have here the client application, we have the proxy, and we have only for this example only two physical hosts that run in a shared multi-tenant environment cache nodes. So as you can see, we have different number of cache nodes of every physical host. And the reason is that because every cache node can process different amount of usage. Now, as I mentioned before, we are responsible to monitor very closely the hardware utilization on each of the physical hosts to make sure that you have enough capacity. So in this example, we see that we bridge to some network and CPU and memory and CPU utilization, and we need to start move things around to make sure that you have enough capacity. So we have multiple different options to do. The first one called heat management. The purpose of heat management is to run across the entire fleet of the physical host and to categorize them for which of them are considered hot and which of them are cold. And then we can decide which of the cache nodes needs to be moved to the other physical host. So in this example, you can see that one of the physical hosts reached to some threshold, and the heat management located that, and now we start to perform the algorithm that we use the power of the two random choices. So we always move the second hottest node and not the first one. The reason that we don't move the first one is because the first one probably is going under very heavy load and is probably going through scale out, and we don't want to interrupt them, but we still need to find a cache node that once we move him to a different physical host, it will release enough resources. So once we move them to a different physical host, we start to relieve some pressure from the original physical host, and this way we keep our fleet balanced and make sure that you have enough resources to run your workloads. But in some of the cases, there are bursts of workloads that kicks in. For example, on live events, or unexpected bursts of workloads and pickups. And you're expecting from us to have the ability to digest and to process these spiky workloads very effectively. And as Abhi mentioned, we invest a lot this year to make our serverless even much more faster than it was when we launched it. So let's dive in. So we are using the platform technology that does not have fixed memory or CPU footprint and allow us to scale up and down very quickly and easily. This technology will deliver a very good performance without compromising on the cost because we are using the oversubscription techniques. So it's actually allow us to instantly grow and shrink our compute in place. It provides us the extra memory, CPU, and network bandwidths when we need to rescale and reshard it. So the ability for us to do that is allow us to make sure that we can have instantly scaling our support by 8 times, and so we can jump from 30K, for example, to 230K RPS, request per second, in just 5 seconds. So when a workload kicks in, we can have the ability to digest it very quickly. Now, that was the vertical scaling. Let's talk about the horizontal scaling. The horizontal scaling had 3 main stages. The first one is detection. And as I mentioned before, we are constantly monitoring the cache node and the physical nodes, making sure that you have enough resources for you to run your workloads. But not only that, we also have the ability to project the future demanding by monitoring the usage pattern, and we use it to predict the usage that's going to happen in the few next minutes. So we can actually scale the cluster ahead of time, and once the workloads kicks in, we already have the capacity to digest the workloads. The second phase called provisioning, and we can provision a new node and attach it to the cluster within a minute. And the way we do that, we are using the warm pooling techniques. The warm pooling techniques is we have a list of cache nodes pre-installed on standby mode, ready to be attached to existing cluster. So, for example, if we reach to some CPU threshold, we can dynamically and very quickly add the cache node to the existing cluster, attach them, and then they can be part of the cluster very quickly. Now we reach to the last phase of the scaling. The last phase called data rebalancing. It's the fact that we need now to move the data to the new shard that was attached to the cluster. So the way that the data stored on ElastiCache is divided by slots. Each of the slots presents a range of data. So we start to move the data from the original slot, from the original shard to the new shard. And the way that we do that is because we're monitoring the usage per slot level. So we can determine which of the slots consider more hot than the others. And then we can balance the cluster itself. So this year we also introduced the ability to move multiple different slots, range of data, in parallel to multiple different targets. So we can actually double the support of requests per second between the 2 to 3 minutes, which is an amazing result. Now I want to talk about connectivity. So we decided to build a single logical entry point to the ElastiCache serverless product. And for that we built a proxy. And the proxy enables us to abstract any changes in the underlying cluster topology. So anything related to scaling, failing, patching, disconnection, everything is hidden from the client itself. The proxy takes care of all of that. The main job of the proxy is to route the request to the correct shard. And the way he do that, he constantly monitors the cluster topology. He has kind of the distributed topology table and make sure that the topology table is already up to date. So we are removing the responsibility from managing that from the client side. We take care of all that. So the proxy, with all this technology, allows us to support huge scale of hundreds of connections behind the scene, while we require for the client to manage only a single connection. And with all of that, it can also benefit a huge scale of throughput. As Abby mentioned before, we can jump from 0 to 5 million requests per second in 30 minutes. Now, if your application is latency sensitive and has no strong consistency requirement, you can get a microseconds response time when you're using ElastiCache Serverless. ElastiCache Serverless have 2 replicas built in the system. You don't need to configure that. It's coming in with the product itself, but it's done mainly for high availability. But it also can increase your read throughput and achieve the microseconds response time. How we do that? The proxy provides a single entry point to the replica itself, and it always promises you to read from the local AZ. If you define your channel to work with read from replica, the proxy, no matter what, if the replica is busy or the primary is busy, it will always look for the closest nodes in the same AZ to read the data, so you can achieve the microseconds response time. You don't need to do anything on the configuration of the server side. You just need to configure the channel, the TCP connection that you established to the ElastiCache Serverless to work with read from replica option. Let's see how you do it. In this simple code of example, you see that I'm connecting to the serverless. I'm using only single connection, while behind the scenes I might have multiple different connections. I'm using TLS because TLS is the default and this is the only option to work with serverless. And I'm also toggling on the read from replica. So in that channel that I'm just established to the cluster, the proxy will promise me to read the data always from the local AZ if there is an option for that. Now you can see I have here 3 blocks, very simple blocks of code. The first one is just populating the data into the cache in a for loop. The second and the third one is reading the data from the cache. The first one is in a for loop, the second one is a batch using a pipeline. What's happening behind the scene is that all these requests go through the proxy spread the request across the shards, making sure that if there is any failure, any connection, any scaling happening in parallel, it promises us for a seamless experience. But not only that, it also promises us to read the data from the local AZ. And as you can see, the code is very simple. We don't need to deal with any of that. The code is simple. Everything is offloaded to the proxy itself, and we can keep our business logic only on the client side. Now I want to talk about the cache node itself and to dive deep about the technology we invest in that area. But for that, I want first to introduce Valkey. This year, Amazon ElastiCache and MemoryDB announced the support of the third open source engine called Valkey. Valkey is high-performance, key-value data store, and it's a community replacement for Redis. It's built by the existing Redis open source contributors, and it dropped in replacement for Redis open source 7.2. It's hosted by the Linux Foundation, which promised that Valkey will stay open source forever. So let's go through the history first. Valkey and Redis open source started as a single-threaded architecture. What does it mean? Very simple. We are waiting for the command. Once the command received, we're reading the data from the network. Then we process the command itself, we are doing whatever the command requests us to do. And then we send back the response. That's it, and this is the event loop, very simple. And why design like that? The main reason is the simplicity. There's no race conditions, no synchronization needed. You can benefit from shared nothing architecture when you scale out, and of course you improve the cache coherency. But with this technology, you can achieve around 200K requests per second, and most of the time we're going to spend on the I/O, on read and write. Let's visualize it. What's happening in the reality? So this is the main thread. Is working and processing data, and then we add in more clients to digest the data. So every time I'm adding more and more clients, they are staying in the queue because they are waiting for the slowest command to be processed. This is a single-threaded architecture. And eventually what's happening here is that we face the head-of-line blocking problem that we are waiting for the slowest client process to be completed. Later, the I/O threads were introduced, and the job of the I/O threads is to offload the I/O to different threads. So it's improved the I/O processing time because it's offload the I/O process time, but this technology still does not allow us to dynamically add and remove I/O threads according to the workload itself. So with this technology, we were able to reach to around 400K requests per second. And this time, most of the time that we're going to wait will be on the process command. And of course, the reason is because the I/O already offloaded to different threads, and now we are most of the time going to wait on the process command itself. There are other problems in this architecture. You see the wait in the diagram. The wait means that every time that we are offloading the I/O, the main thread is kindly idle and just waiting for them to finish. So there we have actually extra time that we can spend and improve the performance. So this year, AWS contribute the new threading architecture for Valkey to unlock the 1 million requests per second for single instance. This is an amazing contribution, and we do that by 3 major aspects. The first one is the asynchronous I/O threading that enable parallel processing of command and I/O operation. The second one is intelligent course utilization that distribute the I/O task across multiple core based on the real-time usage. And the last one is the command batching that optimize the memory access pattern by prefetching access data to minimize the CPU cache miss. So the way it works, we have now the main thread that spawned IO threads according to the workloads, and he can add and remove them as he needed. He also responsible to make sure there is no synchronization issue, because he will constantly keep the affinity between the client's connection and the IO thread itself. And he will make sure that each of the IO threads have enough workloads to digest, so we can utilize perfectly the hardware. And with that, we can achieve the 1 million requests per second. So let's visualize that. We have the main thread now and the IO thread that digesting more and more data that kicks in. And eventually, we can do all of that in parallel. We can also remove some of the IO threads once the workload is become more relaxed. So let's see how everything is now playing together with this technology, with the serverless technology and with the Valkey and IO threads technology that I mentioned. So we have here the proxy, we have the clients, we have the warm pooling, waiting, we have the physical host, and just for this example, I'm spotting in about only a single cache node that have only CPU attached, means that you have only 2 IO threads to digest the steady state workloads. Let's assume that we are running 30K of workloads, and at some point we have some viral live event or some unexpected workloads that come in, and we jump for 230K requests per second. So immediately what we do, we scale up the cache node, we add more CPUs assigned to this cache node, including the memory that this cache node is consuming on the multi-tenant environment. We add in more IO thread to digest the workload, so we can jump by 8 times in only 5 seconds. Right after that, we're going to ask from the warm pool, please assign more physical hosts to the cluster so we can attach them very quickly and start the scale out process. At that moment, the proxy will identify them and they will be attached to the cluster. All the data rebalancing will be work and move the data concurrently between the shards, so we have more resources to digest the workload. So eventually, with all this technology, we can double the supported RPS between 2-3 minutes. We can jump from 0 to 5 requests per second in 30 minutes, and we can support scaling of 8 times throughput in just 5 seconds. Now I want to show you a very cool and short demo. We started with a steady state of 250 requests per second running, and we slowly add in more and more clients and more connections. So you will see the growth of the transaction per second diagram, how we can very easily, quickly digest more and more workloads. As you can see, the P50 latency is a bit jumpy, but we still stand behind less than the milliseconds latency, P50 latency. We are still on the microseconds level. And on the P99, we see some jump to 3 milliseconds because every time that we add in more workloads until the system will get to some saturation level. And what is nice in that is we are still keeping the read latency on the microseconds, and you see how we can jump on the until we reach to the 3 million transactions per second. Just before we finish, I want to give you a few good best practices how to benefit more from your ElastiCache serverless. The first one, we always recommend to use a long-lived connection for the best performance. It's very important to know that creating TCP connection is a potentially expensive operation compared to any typical Valkey commands. For example, handling simple get and set command is an order of magnitude faster when we are reusing existing connection. We also talked about read from replica. If you want to scale your read throughput and you want to achieve the microseconds response time, you need to use read from replica. You also should avoid from using expensive command that scan the entire engine, so it will not be busy. And of course, to limit your large object because it can affect the network exceeded and the CPU cycles to process them. And if you are using a serverless, ElastiCache serverless for the caching, it's very common to use time to live to manage your cache size. It's, of course, when you define the time to leave, it's per item and not globally. We also recommend to use all the relative option or the fixed option for deletion them. But the most important is to use the random jitter, so you can spread the deletion across multiple different sliding window and not put all the deletion at once and put more pressure on the ElastiCache servers. That's it. I hope you enjoyed the session. We'll get back to Abhay.
Thanks, Yaron. Hopefully you found that interesting and learned some interesting new ways on how we're using the multi-threaded architecture to scale faster. Thank you for coming and thanks for taking the time. I encourage you to please take the survey in your reInvent apps. That helps us get feedback about us as speakers, about the content, and give you better presentations over time. So please take that survey. We are a little early, so we will hang out outside, and if you guys have any questions, happy to answer them. So yeah, feel free to catch us outside and happy to answer those questions. But thank you so much for taking the time and welcome.